Good evening, sir.
Yeah, good evening, everyone. So this will be a open session for week two. So if you have any doubts first, you can ask that. Any doubts in the contents of the week two? Have you gone through it?
Yes, sir.
Yeah, Akshay, what about you?
Sir. Yes, sir. I've gone through like the first three videos only so far.
Okay. So okay, so if you don't have any doubts, I'll just quickly go through the overall contents of the week two. So week two mostly involves the most important parts of the week two is just representing things in computers. Right? You may you have these things like number representation, different types of numbers. Basically, first is integers, assigned integers, unsigned integers. So these are just numbers, and then you have different uh, number systems like hexadecimal representations and binary representation and how it's right. So important thing is computer can only represent things in binary, which means zeros and ones, that we know. But how we can represent different things in with zeros and ones. So that's the whole point of the week 2. So we need to represent text, which is some text, right? So text also should be represented in some form of zeros and ones. So how do we do that? That's what the whole week deals about. And also there are instructions that need to be encoded in some format, right? Instructions sense all the instructions for a computer. So usually every computer will have instructions like add, move this value to that, every value, the control, the arithmetic things, like and comparing things, everything will be an instruction to a computer, right? So every computer generally will have a set of instructions, and every instructions will have some operands. So like addition will have two things to add, right? So they are called operands. And if you want to move something, some value to another place, we need a place to move and place to take from. So that things. So those are operands for an instruction. So there are multiple things that we need to just oh. So first thing we have is numbers, right? We need to represent numbers. And what are the different types of numbers that we have? Usually first unsigned numbers, which will start from 0, 1, 2, 3, etc. Right? These are the unsigned numbers from 0 to. And then we have signed numbers, which are like -1, -2, -4. And then we have floating point numbers. So there are multiple ways to represent the real numbers. So you may have seen numbers like 2.3, 3.25. These are real numbers, right? So there are some methods to it. So these are unsigned numbers. These are signed numbers. And there are real numbers. So how do we represent these real numbers? So there are multiple ways. One of those ways are fixed point notation. So there are some conventions, right? And floating point notation. And then we have text in general terms, which is we call in C or multiple programming languages characters. A character refers to a single letter of a thing. Text refers to whole thing. In most programming languages, this group of characters is also called as a string. It's also called as string in multiple languages, right? These are also called as strings in some programming languages, right? Then what we have, it's like example A, B, all those characters like this, everything that will appear on your keyboard, right? Space is also a character, kind of that. And then so this text is a group of characters, right? Characters. And then what we have, the thing that we need to represent is instruction. Instructions. So every instructions, so you write a C program, right? So it's a C course, you may have seen some programs. So all these programs in different languages that finally gets compiled to the set of machine instructions. So assume you have a computer, and that computer can understand only a specific set of instructions which are encoded in bits. Bits in the sense zeros and ones. So every compiler that you have, so you may be aware of the compiler. So what a compiler does, compiler takes in the source code, which is the source code C code you write, and then converts it into a set of instructions that would execute your code so that the machine would understand it. So all those final instructions which will go into the computer after compilation will be in a certain form. So each machine, so based on your computer, the processor, the type of the processor your computer have, every processor will have its own set of instruction set. One set of instructions is called as instruction set. So they have some instruction set, the set of instructions. So assume my computer only supports. So known as this is a very full-fledged computer. It's a very minimal version of a computer that only supports addition and subtraction. So the two commands that my computer supports are addition, add, and subtract. I can name my instructions, right? So these are the instructions my computer supports. My the imaginary computer. So these are the two instructions. Maybe loading the values from registers to thing. This may be also the case. Just a minute, I will check the results setting. So we have this kind of set of restrictions. So how do we represent anything in computers? Okay. So usually to represent n number of things, so we have, assume we have some n number of things that we want to represent. So we have to represent it through bits. So you may have heard of this binary number system, right? Binary number system. So binary number system, each binary number will be a set of ones or zeros, something like that. And we know that this number system starts from 1, 0, 1, 0, 1, 0, 1, 1, and 1 double 0. It goes like this, right? So what does this number corresponds to? So we know that this corresponds to, each number corresponds to its one natural number, one integer kind of thing, right? So it will be 0 and it will be 1 in, so I'm writing it in decimal. Decimal 0, 1, 2. So corresponding value for 2 is 1, 0 in binary, right? 2, 4, 3, 4, 5. So you can see this is 3, 1, 1 is 3, and 1, 0, 0 is 4. And there is way to convert this based on the powers of 2. You may have learned this, how to convert a binary number to this. So you are saying for each digit, you are saying a power of 2, and then add if the power of 2 if it is 1, and not add that power of 2 if it is 0. So for example, to convert a number from binary to decimal, how do we do? So consider this is the number. So we are saying the power of 2 for each of this number, starting from 2 power 0, which is 1, and then so start this. So this is 1, 2 power 0 and 1. So we add this. 2 power 1 is 0, so we don't add that. 2 power 2 is 1, so 2 power 2 is 4. So we add that. And 2 power 5, we don't add. 2 power 4, we don't add. So sorry, 0, 1, 2, 3. 2 power 3, we don't add. 2 power 4, we don't add. And 2 power 5. So 2 power 5 is 2 power 5 is 32. Yeah, 32. So 32 plus. So mostly while you are practicing, if you find converting these numbers are hard, so for the practice problems, you can always go, and every system will have calculator. So in Windows, you may see in the settings there will be a programmer's calculator option is available. In my system, there is this numeral mode. So this mode will be available in most of the system calculators. So there you can convert between these different modes. So for example, our number is 32 plus 4 plus 3, which is 37, right? So if I put 37, I can see it's the binary value of this here. And you can also enter binary and convert that easily back to different number systems. So these are the most common number systems that we use: binary, octal, decimal, hexadecimal. So usually people who use this binary things for coding in the olden days, they used to use this calculator. And since now today, these days also, we need for something this calculator, this programmer's calculator may be useful for some cases, because when we are dealing with very low level programming, this will be very helpful for us. So take a note of that. So okay, so this is numbers, right? So how do we? So now we saw how we represent numbers in the normal form. So the normal number starting from 0, we can represent in this way. So then there comes a problem. How do I represent negative numbers? So still then, till now, anyone has a doubt? Any doubts, or can I proceed with negative? Any doubts, anyone?
Sir?
Yeah?
Sir, can you please explain again how to convert?
Yeah.
In
Just binary to
yes, sir,
calculator.
Because I'm not getting the option.
Okay, I think in Windows there will be an option called as programmer's mode in. Let me check. Programmer mode will be there. So in Windows calculator, I think, yeah, there will be some few modes. So here this scientific mode will be there. If you click here, you can see the programmer's mode. Here this. Are you able to see it? In the calculator app? Are you able to see this programmer mode?
Yes, sir. Yes, sir. Yes, sir.
Yeah. Okay. But you should also know how to calculate this, because in the exam you will have a calculator, but not this programming calculator, I think. Sometimes you may not have a calculator also. So you should be aware of how to convert it manually. Yeah. Just to verify for practicing, you can do that. Yeah. So okay. Now, okay. So this is the normal. So now we have numbers. So assume I need 5 numbers. I need to represent 5 numbers. So what are the 5 numbers? Starting from 0, 1, 2, 3, 4. So these are 5 numbers. Okay. So you can see that here, till 2 numbers, we only needed 1 bit. So 1 bit means bit is binary digit. Shortly called as bit, right? So to represent 2 numbers, 1 bit is enough. And you can see to represent 4 numbers, 2 bits are enough. But with 3 bits, how many numbers we can represent? 3 bits, how many numbers we can represent? 101. All different combinations will come, right? So it's like permutation and combination. You may have heard of that the math class if you are there. So what are the different possible ways that we can set up zeros and ones? So that's what this
Totally
is.
8, sir.
Yeah, so that will be equal to, so the different number of different possible values that you can generate with 3 bits is 2 power 3. 3 bits will be 2 power 3, and it will be general for n bits. With n bits, you can represent up to 2 power n values. Okay, so now we are representing the normal integers, right? So how we are representing? So starting from 0. So starting from 0, if you want to represent 2 power 3 numbers, then what will be the last number? Because since we are starting from 0, it will be 2 power 3 minus 1, right? Because of we are including 0 also. So 2 power 3 is 8. So with 3 bits, we can represent 8 unique numbers. But if we are starting from 0, we can represent only up to 7. Because 0 also has 1 value, right? So that's how 2 power n minus 1. So this power 2 power n minus 1. So with the so quickly answer this. So if we have 5 bits and we are going to represent numbers from 0 to how many, which is the last number that we can represent with 5 bits?
Sir, is it 32?
It's not 32 because 2 power 5 minus 1, because we are starting from 0, right?
Oh, okay, sir.
So totally we can represent 32 numbers, but if we are starting from 0, we can represent up to only 31.
Okay, sir. Got it, sir.
You can see this, right? So with only 1 bit, you can represent 2 numbers, but starting from 0, the second number will be 1, right? So you can represent up to 1 only with 1 bit. With 2 bits, this is 3 actually, right? 2 power 2 minus 1, because we are starting from 0. We are starting to represent from 0. So that's why that minus 1 is there. So the last number would be 31. So 0 to 31, there will be 32 numbers you can represent. But the last value will be 31 since we are starting from 0. So now let's go on about negative numbers. So to represent negative numbers, we have 2 conventions. So it's not like there is no negative thing in binary because 0 and 1. So we need something to represent this minus. So there is this minus sign is there, right? Minus. So I say whatever number is there. So for example, I have minus 3. I represent 3, which is this, right? 3 in binary, and this thing. And a bit before, I put 0 if it is positive and 1 if it is negative. So this is my convention. So what my convention says is this first bit will be used to represent the sign. Since the signs can be either minus or plus, there are 2 values, right? So we just need 1 bit to represent that 2 values, minus or plus, correct? So there are 2 values, so 1 bit is enough to represent. So this will be minus 3 and this will be 3. So 3 will be represented like this. I say this first bit, this most significant bit. People call this this left side bit as most significant bit, and this left side bit is least significant bit. Why most and least? So you saw that conversion from this, right? So this value will get 2 power 0, which is the least value, least significant, and this right side value will get the highest power of 2, right? So it's most significant. That's why people say that it's most significant bit and least significant bit. And you can see this is how we represent. So this type of representing the numbers is called signed magnitude representation. Signed representation. Okay. And there is another format which is called as floating point representation. Oh, so sorry. not floating point. It is called as 2's complement notation. Why we need 2's complement notation? So there is a small drawback in the sign magnitude. So since we are representing numbers from 0, so how we represent 0? 0, 0, 0, right? With 3 bits. If I am using 3 bits, I can represent 0 like this. But what about minus 0? It's also 1, 0, 0. Right? It's still 0 because I am saying in my convention that this bit will represent the sign. So if this is representing a sign, this is also equal to 0 and this is also equal to 0. So we have 2 representations for 0.
Sir, but minus 0 is not possible.
Yeah, minus 0. But here it is possible, right? You can represent in. So I said that convention. What my convention is, first these 2 bits will represent the value and this will represent the sign, right? I can put it.
Sir, so in low level language, minus 0 exists, sir.
So it's not like minus 0 exists. So, okay, let me tell you. So see this from this point. So now I am representing some number. So this number, I said some rules, right? How to convert the minus number. So I said some rules. So in,
Yes,
in
sir.
those rules, with those rules, if you are interpreting with those rules, what will be the answer? This is representing minus 0, right?
Yes,
Minus
sir.
0 in mathematical terms will be also 0. Same as 0. Minus 0 and plus 0 is same as 0, right? Same value.
Yes, sir.
It's both the same value. So what it has is this is also equal to 0. But the representation, it has 2 representations for the same value. For other numbers, it has only one representation. 3 has only this representation. Minus 3 has only this representation. But 0 has this representation and also this representation. So usually people don't use this in computers nowadays. Let me put it like this.
Sir, then how can we represent minus 2?
Minus?
Minus 2.
Minus 2. So how in this notation, in this representation, what will be minus 2? Minus 2 will be, so how do you represent 2? 2 is just 1, 0, right? And here minus will be 1. For minus I put 1, for 2 I put 1, 0. Right? So this is minus 2 in this signed magnitude representation. Signed magnitude means sign, this one. Magnitude means value. So this is the value. So that's why we call this as signed magnitude representation. So to tackle this disadvantage, this confusion problem, people introduce this 2's complement notation. So that's why this 2's complement notation was introduced. So here we only have one representation for 0. So this will be 0. So how do we represent negative numbers? So there is some rules for this. So let me tell you. So okay. Yeah. So to represent, so how it will be arranged is, so assume I use 3 bits. So I am going to use 3 bits to represent minus negative numbers and this, right? So in the signed magnitude notation, what is the lowest number I can represent with 3 bits? Can anyone tell? What is the smallest number I can represent with this?
7-bit.
No, with 3 bits. Only 3 bits should be there. What is the smallest number that I can represent?
0, 0, 0, sir.
Negative numbers is also there, right? So you have to say the least number, lowest value. What is the very lowest negative number that I can represent?
Minus infinity.
No, I cannot go minus infinity, right? So what?
Sir,
Only
0.
2. So you see, only 2 bits we are using for value, right? So
Yes,
with
sir.
2 bits, what is the biggest value that you can have? 0, 1, 2, 3, right?
Yes, sir.
3 is the biggest value that you can have with 2 bits. you can see this here with the 2 bits. 0, this is 1 bit. 1 bit, 2 is the highest, this 1 is the highest value with 1 bit. With 2 bits, 3 is the highest value. So 3 is the
Sir,
highest
is
value.
it
So,
4?
sorry. So the smallest value will be 3 minus 3 and the biggest value will be 3. So this is the range. You can see, right? With this representation, this signed magnitude representation, the smallest number will be minus 2 power n minus 1 to 2 power n minus 1. So for example, if n is equal to 2 with 2 bits is, so sorry. If you are considering 3 bits, so sign also needs 1 bit, right? So in that case, you also put n minus 1 here in the bracket. So sign needs 1 bit. So that's why we are reducing. So this may look complicated, but once you understand this, this is very simple. So you see, we are having 3 bits, right? But 1 bit will be used for sign, correct? So with 3 bits, how many different numbers we can represent? 8. That's what we saw in the previous thing, right? 2 power 3 is 8. So you see, minus 3, minus 2, minus 1, 0, 1, 2, 3. How many numbers are there? 7 numbers are there, right? Since
Yes,
we
sir.
have two representations for 0, there is another representation for 0 also exists. Correct? Correct? So there are
Yes, sir.
actually 8 values we are representing. So this is, so why we have n minus 1 here? Because that 1 bit is used for sign. So leaving that 1 bit, so if we have 3 bits to represent, leaving that 1 bit, how many, with that bits only we represent the number, right? So what is the biggest number I can represent with n minus 1 bit? 2 power n. N minus 1. 2 power n minus 1. With n minus 1 bit, I can represent 2 power n minus 1 bits. Correct. So why this minus 1 is there? Since we have that 0. That's why we minus 1 is here. We are taking 2 values for 0. That's why we couldn't represent minus 4, 2 plus 4. Because we have 0, 2 zeros middle. Correct.
Yes, sir.
That's why this minus 1 is coming. So then, for example, if we have 4 bits, what will be the smallest number with 4 bits? What is the smallest number and what's the biggest number with signed magnitude form?
So minus 32 to plus 32.
How minus 32? So 4
So
bits are
because
there. 1 bit will be used for sign, and then 3 bits will be there. Correct?
so that's what, sir. 4 minus 1 is 3. So minus 2 to the power 3, it becomes 32.
2 to the power 3, how 32? 2 to the power 3 is 8
Sorry, sir.
only,
8,
right?
8, sir. 8, sir. Sorry, sir. Minus 8 to plus 8.
So minus 8.
So actually, one more thing here. Here it will be. I should put this minus in this bracket. Yeah.
So it's a minus 8 to plus 7.
Yeah. So it's not minus 8. It's actually minus 7 to plus 7.
How, sir?
Okay.
Minus 7 to plus 7, because the same value should be there, right? Because minus 3 to plus 3, because we have 2 values for 0.
Okay, sir. Okay, sir. Understood. Understood.
That's why we have. So minus 7 to plus 7 we can represent with 4 bits. Okay. And okay, this is the signed magnitude representation. So this 2 representation is going for waste, right? So people come up with another representation that is called 2's complement representation. So here, what they did is, with the, for example, with the 4 bits, let's assume 3 bits for now. So what they did is, they started from 0. They put it up like this: 0, 1, 2, 3, So with the 2 power 3 bits, how many represent? I can represent up to 8 numbers, right? Then they started with this -4, -3, -2, -1. They arranged numbers like this. So why they arrange the numbers in this order, like going forward from 0 to 3 and going in a reverse order from -4 to this? So let us check. So now, why they represent it like this is, for example, I want to same as that. So this will be similar to that. So if I want to represent minus 1, what is it is, I write 1 with these 3 bits, with how it will be 0, 1, 0, 0, 1, right? With these 3 bits, 1 will be there like this. Then they introduced one two-step process, 2's complement. So what is a 2's complement? 2's complement, to find a 2's complement, we should invert this bits. So invert this bits means, how do we invert this bits? Inverting means changing 1 to 0 and 0 to 1. So I convert this 1, 0, 0, 1, 1, 0. And then I add a 1 to it. So if I add 1, what this number will become? This number will become 1, 1, 1. So you assume these numbers are arranged in this order: 2, 3, 4, 5, 6, 7, 8. So sorry, 7 only, 0 to 7, 8 numbers. So now what is this 7? Actually, that is 1, 1, 1. Correct? So that's where we place this -1. So this two-step process is, to find negative number, you represent it as positive, change all bits, add 1, and put it in that place. So this is how people started representing the negative numbers. What is the advantage here? Here we have only one representation for 0. For example, in this -4, if I want to represent -4, what I will do? -4. So I will write 4 first. How 4 will be? 1, 0, 0. This is 4, right? This is 4. And I change all the bits. Then it will be 0, 1, 1. Correct? And now I add a 1 to it. So what it will become? It will become, so when we add 1 to 1, the number will become 0 and the 1 will go to the carry. We add it on the next number. So then the 1, 1 will be there, and that will add it on 1, 0, and it will become this. So for example, this is binary for 3, right? Add 1, that will become binary for 4. But actually, this 4, what is the fourth number here? It's -4. So this seems, while this seems confusing, you can assume that all the positive numbers, if we started representing in this in binary terms, you can see all the positive numbers will have the most significant bit as 0. So I am going to represent each of this so each of these numbers in binary format. So it will be 0, 0, 0, right? Okay, let me write it this way, so then it will be clear. I'll write these 8 numbers in binary format, the normal binary conversion, and then also the 2's complement. So first number is 0, 0, 0, which is 0, and it is here also it is 0, right? And 0, 0, 1. Here also it's 1. Here also it's 1. 0, 0, 1, 0, which is 2. Here also 2. 0, 0, 0, 1, 1, which is 3. And here also it's 3. This part is same, right? But here comes the change. So what is the next number after this? 1, right? 1, 0, 0. So there it will be not usually 4, and here it will be -4. This number will be in 2's complement notation. So similarly, 5 will be like this. 5 will be -3 in this notation. it will go like this. So how to convert? So did you understand this step procedure, this 2's complement procedure?
Yes,
Sir,
sir.
how is it 110, sir?
What 110?
-1.
Oh, this one.
Yes,
Yeah,
sir.
I'll do this. So to convert, so if you want to represent -1 with 2's complement, what you do is first represent 1. Usually 1 will be like this one, right?
Yes, sir.
So this,
001.
and then change all the bits 1 to 0 and 0 to 1. So then you will get this, right?
Oh, okay, sir. Okay, sir. I thought you were changing the order.
No, not changing the order. Change each one, all the 1 to 0 and all the 0 to 1.
Okay, sir. Understood now.
Then you add, then you get the number. And this is the binary representation for -1. This 111. Right? So that's how we are going to represent the numbers. So do you get this? How numbers are represented?
Sir, understood.
Yeah. So let me give you one more practice. So can you convert this number? So numbers are represented with 4 bits. So the number is, sorry. So what number does it represent? Can anyone find? How to do that? So I showed from this to finding the representation. But how do you find from this to the original representation? There is a trick. So you see, all the negative numbers will have the 1 in here, right? So you can see that this is a negative number. So what you do, again do the same step with this. These steps I told, right? Inverting and adding 1. So that will give you the actual number again, like the positive part. So how will you do that? Can you tell? So changing the bits, which means 0, 1, 0, 1. Add 1 to it. Then what will happen? It will be like 0, 0, 1, 0. Correct? So what is this number? Usually what is this number? 2 power 1 and 2 power 2. Which is 2 plus 4, which is 6. So actually, since this is 1, this number is actually -6. So let's see how we go back to -6 to this. So -6 will be this number, right? So usually 6 will be this number. So to convert -6 to this 2's complement notation, we'll write 6 like this. So 6 equal to this. And we'll change the bits. How it will be 1001, right? And we'll add 1 to it. Correct? And then what will be the answer? It will be 1010. You see, this number is coming back.
Sir, but 0110 is 6, sir. How is it -6?
So this is -6. Since we are using 4 digits, this one causes is the -6. So this is not -6.
Okay, sir. I thought that was -6.
No, this is -6. So when we minus the minus, we will get the plus, right? So that's how we get the plus number. So to know which number is this, we again do the same step and we'll get the positive of that. We know that this is a negative number because it has this 1. So we put that negative on top of this positive number. Okay.
Okay,
We can also check this. So I think this calculators use this notation only. So if you put minus, I'll clear this, and minus what number we put? -6. Yeah, -6. What happened? Okay, it's representing in a very long format. Don't consider the 1. See the last things. This 4 bits. 4 bits you can see, right?
Sir, why is it in a long format?
So it's representing numbers with so many bits. many bits, correct? So we are only representing the number with 4 bits. So we should see only the first 4. If you represent that number with this many bits, this will be the representation for -6. Okay. Here we don't have a setting to say how many bits you should represent. So here you can see it is representing with 4, 8, 16, and then 16, one more 16, and some more bits. So like 40 bits or something. Okay, that's right. So if you do this with 40 bits, this is the result what you get. If you do with this 4 bits, this is the result you get. So what is the advantage here? You can represent from 0, this 2 power minus 1, right? This is 2 power n minus 1. For example, yeah, this part. Here, this will be -1 only. The positive part, you will go 0 to n minus 1. But in the negative part, this minus will be not there. In Bruce complement notation, you will have this part, this -1 will be there, but this -1 will not be there. Why? Because we can represent up to -2 power n, that n minus 1. Correct? Here from 0 to 3 only, but -1 to 4 we can represent because the one more 0 we got rid of. Correct? Okay, another small example. So what? Okay, can you find the value of -3 with these 3 bits? How would you do? Anyone? Can you quickly solve and say me the answer? -3 with the 3 bits. How you can represent?
The -3 is 101, sir.
Okay, 1, 0, 1. So let's take this back, convert this back again, and check whether this is wrong. Or else we can also easily verify using these values. For simple thing, we can use this. For example, actually -3 would be equivalent to this 5. So this is actually the value of 5. That is one way to verify that. Other way to verify that is, so this is -3. So we convert this to positive by inverting this,
0,
adding
1, 0,
1. Yeah, we'll check. We are going to check this whether this is -3 or not. So when we do that, we'll get the value of 3. Correct. So when we do something on inverting on this -3, we'll get 3. So which means, yeah, that is actually this is -3 only. So that's way you can also verify that. You can do the same thing to reverse verify.
Sir, so internally, always -4 is mapped to 4, -3 is mapped to 5. That is how
No.
configured is.
No. Only when we are using 3 bits. So when we are using 4 bits, how it will look like is, when we are using 4 bits, it will look like 0, 1, 1, 2, 3, 4, 5, 6, 7, -8, -7, -6. You can also try with this 4 bits and explore how the numbers, this changing part you can try. So now what we saw with 4 bits, let's check what is the value of 3, -3. Okay, with 4 bits. -3 will be how it will be. So 3 is 0, 1, 0, 0, 1, 1, right? So this is this is 3, correct? This is 3. I am inverting it. So 1, 1, 0, 0, correct? And then I am adding 1. So what it will be? 1, 1, 0, correct? So what do you think this value will be? 1 or 4, 5, plus 8. So 5 plus 8 is 13, right? So 0, 1, 8, 7, 8, 9, 10, 11, 12, 13. Correct? So this will be minus 3. So this is how 2's complement notation places the numbers. So
Okay.
with that many number of bits, you can represent a larger range. And what is that range? 2 power n minus 1 minus 1, this part. Correct? And this 2 power n minus 1 minus 2 power n minus 1. So 4 bits, n minus 1 is 3, minus 2 power 3 is minus 8. Correct?
Yes, sir.
Oh,
Now it's
this
getting
is-
clear, sir.
This is how this is how this numbers be. So this 2's complement notation. So usually computers use this 2's complement notation only. So that's why I didn't show that negative on the calculator. This 2's complement only will be usually used by computers, right? C also, the C language also uses this 2's complementation only. So I have this thing. So uh, so are you aware of this hexadecimal first? Hexadecimal notation. So why this hexadecimal notation is introduced is why it is introduced is, so representing very long numbers in binary is very difficult. Reading also very difficult. So if I do something like this, what is this number? We cannot see it, like read it or something like that. Cannot get how much big it is. We don't, because 0 and 1 only there. We are used to this seeing numbers like 9, 10, so that we can compare easily, right? So what people did is they split this binary number into 4 bits and started representing each 4 bit into a letter. So 4 bits means how many values we can represent? Anyone? With the 4 bits, how many values we can represent?
7 values and 8 numbers, sir.
Values and 8 numbers. Actually 8 numbers. So sorry, 2 power. So with 4 bits, we can represent 2 power 4. What is 2 power 4?
32, sir.
2 power 4 is 16. 2, 4, 8, 16.
Okay, sir.
2 power 4 is 16. So we can represent 16 values. So in our normal number system, what are the digits we have? 0 to 9 only, right? So 10 digits are there. But we need 16 digits. So what they did is, after 9, they put A, and then B, then C, then D, then E, and F. So now what we have? 16 digits. So all the numbers from 0 to 15, 16 digits. So 0 to F. So it's no more 0 to 9. In hexadecimal, you also have till F. So A is equivalent to 10, B is equivalent to 11, C is equal to 12, 13, 14, 15. 0 to 15. Total 16 numbers we can represent. So what people did is started converting. So let me change this values. So now, what does this represent? 2 plus 8, which is 10. 10 means A, right? This is 2 plus 4 plus 8, which is 14. 14 is E. Have 0 here. So now it's just 3, right? 3. So we write this number as 3EA. Now we can easily see that this is a big number, and we can also compare numbers. So 3DA. So can you say which number is bigger, 3EA or 3DA? Which number is bigger?
DA, sir.
This is bigger because you can see D is smaller than E, right?
Yes, sir.
D is smaller than E, which means this is smaller than that.
Oh, yes, sir. Yes, sir. 3A only.
Yeah. So how do you do like this? So you say 309 and 319, which is the smallest number.
309.
This is, yeah, similar like that. So you can compare, you can easily see what is that number, kind of get it right.
Yes,
So
sir.
that's why people use this number. So it is very short. So here we have 12 digits, but here we have 3 digits. These are hexadecimal digits. So to differentiate, people also write sometimes 0x here. So 0x means it is the next number is the hexadecimal number. So people say it like that. Okay. So everything will be represented in binary for computers, but since humans cannot process binary very easily, humans invented this hexadecimal so that we can easily convert hexadecimal and binary back and forth. This also you can easily convert each digit. Take A, convert it to binary, E, convert it to binary, C, convert it to binary. Okay. So converting back and here to here and there to here will be easy. Okay. So now we saw how numbers are represented. Okay? So these are just normal numbers. So here we can see these things. Int, integer. So C has this types: integer, long integer, unsigned integer kind of things. So integer will use usually 4 bytes of data. Integers will use 4 bytes. So 1 byte is 8 bits. So 4 bytes, 4 bytes, which is 4 into 8 bits, which is 32 bits. So usually the integer data type in C will use 32 bits, and usually when you say only int, it will be signed only. When you want unsigned number, you should specify unsigned. And then short is there, which will use 2 bytes. And char is there, which will use 1 byte, which is 16 bits. This is 8 bits. It will be like that. And long will be, long int will be 8 bytes. This is a normal C. Okay. So about floating point numbers, so there is fixed point and floating point values are there. All you need to know is that, so we don't go very deep in this rotations, converting back and forth from floating point and it, so because it's kind of very difficult to do it by hand. But what you need to know is that the floating point representation, there is this 1 bit used to represent the sign, and there are these 8 bits. So usually floating point will be represented by 32 bits, which is 4 bytes. So floating point also, there we have 2 notations. 32-bit floating point, usually called as float, and 64-bit floating point. We call this as double in C. We call this double in C. So 8 bits will be in 32-bit floating point. I am explaining. 1 bit will be this, 8 bit will be exponent, and the remaining bits. What's the remaining bits? Okay. 23 bits, right? 23 bits will be the magnitude. So something like this. So minus, we represent scientific notation like this, right? 35.24 into 10 power minus 3 or minus 25 or 34, we will do that, right? So what does this mean is, this 1 bit will be used to represent this minus, whether it is minus or plus, it will represent. This 8 bits will be used to represent this number, right? So what is the power? 10 to the power some integer will be there, right? So that integer, this 8 bits will be used to represent. Okay, and then this number is there, right? This number, the 10 to the power thing. So that number, this 23 bits will represent. Okay, so that's how this floating point representation will work. This part will be represented with this 23 bits, and this power part will be represented with this 8 bits, and this 1 bit will be used to represent whether it is minus or plus. Okay, this is for 32-bit floating point representation. And there is also something called as fixed point notation. So in fixed point notation, how we will convert is, so as in fixed point notation, I want to represent this number. So usually in floating normal, so I'll convert this to binary. So how I will convert this to binary usually? Sorry. So it will be represented like this. So 0, 1, so 0, 1, 0, 1, 0.0. If we have something like this, what does this mean is, in fixed point notation, this number, we'll convert it normal like some number, right? Minus or plus that part. And this will be, so here we use 2 power 1, 2 power 2, 2 power 3 to convert it, right? Similarly, we use 2 power minus 1, 2 power minus 2, 2 power minus 3, which is 1 by 2 and 1 by 4 and 1 by 8. Right? So we add up that parts. So here it will be add up to 2 power 1 by 2 plus 1 by 8. So what is 1 by 2? 0.5. What is 1 by 8? 125, right? Which will be equal to 0.625. So what is this number here? So if we are following negative also in fixed point, this will be a sign bit or something, or 2's complement, you can represent it like that. So there are many ways in which the different parts of the number will be represented. So in computers, we mostly use this floating point notation in C. This you convert it to the number, which means like 2 plus 8 plus 32, which will be 41. So it will be 41.165 in fixed point notation. So computers don't use this very frequently. Usually we use floating point notation. That is because that is very easy for computers to do calculations. They represent very small numbers and all. So here you can see numbers less than 1 by 8 we cannot represent easily with this fixed point. But here we can go up to 10 power minus very large number. So very minute number also we can easily represent this floating point. Okay, any doubts?
No doubt, sir.
Yeah. So if we need extra precision, so we want to go very minute level. So here it will go to 10 power some very minus number. Even that number can be very precisely, we can compute using 64-bit. So some very precise computations use 64-bit floating point. Okay. So these are about numbers. Now, how do we represent text? So what is text? Anything that we write here, right? So whatever these things I write here are text. These are not numbers. We don't perform numerical calculation with this. We just represent this. So usually computers use we can represent if I can encode it in a way that I can encode it like A, B, C, D, and up to Z will be the representation. So I can assign 0 to A, 1 to B, 2 to C, 3 to D, and so on, right? I can assign some values like that. Just like in this, we assign the sign the magnitude, we assign the negative numbers to that values, right? Similarly, here also I can assign. But since keyboard has many characters than this, people thought of a way, very standard way, which is called as ASCII. So this is a convention, American standard convention for this. So that's how it goes. And in that convention, the value 65 is assigned to capital A. And it will go like that. 6 will be capital B, and so on. And small letters, this is the lowercase alphabets, starts from 97. Small letter A, and 98 will be B, and so on. And the other parts, the before parts and the in between parts, after parts, that numbers will have these characters and so on. You can see the ASCII table. You can see how the characters are represented. This is the ASCII table. See, you can see there are different characters, right? See, 65 is for A and B, C, D, F, G, H, I, everything is there. And before things, there are some other, this tab, backspace. Every keyboard keys need something, right? So cancel, escape key, you can see them of it. And this characters. See this characters, one, and these numbers have this, numbers are here, and small letters start from 97. Right. So this is the basic ASCII table. So basic ASCII table, it has 0 to 127. So it is 127, which means 2 power 0. 127 is 2 power 8 actually. So they create, this is the ASCII table, and these are the 128 basic characters that computers can represent. So you can see the other language characters also represented by computers. So that is kind of an extension called Unicode, which will have all language characters there. So by default, the char structure won't support that other language things, only support these things which are in the keyboard usually. So that's called ASCII characters. These are called ASCII characters. This is how it is represented. And you may think why 65 is A and 97 is B. These numbers may look like kind of weird numbers. Why did they keep A in the beginning and so on, right? So there is a idea behind it, why it is kept in this way. Let me show. Okay, so the number 65, see, it's in hexadecimal, it's 41. right? And 42, 43 will be B, C, D, E, and so on. And the numbers 97, it's 61, right? And it will go on 62, 63. So they kept it in a way that it would be easier in hexadecimal. But in decimal, it may look a different place. Why this weird number they kept it here for A and here for right. So in hexadecimal, these numbers will look 61 and 41. And similarly, if you see the what is this number for 0, 48, right? So what is 49? Is 49 decimal? It's 31. So 1 is actually 31. So these numbers are placed in 3 and that per corresponding place. 4 and corresponding place, the alphabet starts. 6, the lowercase alphabet starts. Okay. So this way you can see how these numbers are. So totally 128 values, starting from 0 to 127, and each has the corresponding character. Right. This is how C program represents the things. So if we add 5 to this A in C program, it will go 1, 2, 3, 4, 5. Go to F, which is 65 plus 5. You can also see this. I am doing this char A. I am adding 5 to A. So what will be 5 plus A? F. Right? It will be like this. Now you get how this will be represented. Right?
Sir, does this table varies for a program to program?
No. This is a very standard table. This ASCII table is a very standard table followed by this is like kind of universal thing. So
Okay, sir.
some languages, as you can see, Java uses Unicode. So that is extended. But there also the standard ASCII values. So that Unicode values will be after this only. So this first 128 values will be always the same in any programming
Okay, sir.
language. You can see this, right? So this thing about this, as much this, every programming languages has this this only. Only Unicode has the numbers after this.
Okay, sir.
Okay, so this is a very common table, this convention followed by everybody.
Okay, sir.
Okay, so what we haven't represented it, we have represented text, everything. We haven't represented the instructions, right? Yeah, instructions. So if you want to represent multiple characters, we just use more bytes. So 1 byte for 1 character, 2 byte for 2 character, and 3 byte for 3 character, and we go like that. So this is how we usually represent. Byte means 8 bits. Why 8 bits? Just 128 values are there, right? That's why people use 8 bits for a character. The standard table, this ASCII. See that? They can standard correction. You can see this. If I have the character 5, which is from here, if we subtract the value of 0, this character 0, you will get the actual value of 5. Right? 48 minus 53 minus 48 will be 5, right? Then you can have that, convert the character to integer easily. So there is that way of that. And other thing, to convert uppercase value to lowercase value, just have to add 32. So you see, for every common things. So this 72 plus 32 will be 104, which is the lowercase. So converting from lowercase to uppercase is also easy. So that's why they were placed in very standard format. The same corresponding place you can see. This has 128 values, right? 32, 32, 32, 32. And you can see after the next 32, small letter is there. So if you subtract small a and 32, you will get the capital. So to convert capital, you can subtract 32. To convert to small, you can add 32. So that's why they were kept in this very exact places, so that it will be very easy for developers, the people to do this. Right? Okay. So we talked about instructions. So there may be many instructions in some machines. Some machines will have a very small number of instructions that it can do. So what about instructions? That's it. There may be instructions in the sense like do this and do that. Computer have to know every step by step, right? Like take the value. So we have memory and values, right? So put value to memory. So this put is instruction. What value? I should use some number, right? Memory is another place. So how do I represent memory? So this place. So every memory will have an address. So you may have seen in the first week we use generalized computations. So what are generalized computation? We use this kind of notation called as m of 0 and m of 1, right? So this is the first box of the memory and the second box of the memory. So which box? We use a number to represent the box, right? Actually, that number to represent that box is called as address. You say this is address. I have an instruction which is put value to an address. So value can be a number. Address will also be another number, right? So this computer will understand. I'm saying to put that in. And get the value and put it in another, from one address to another address. Put can be also something like address to address. And there can be another commands like add this value and that value, value 1, value 2, and put it into some address. Add these values and put it in that address, or else add the value with the value in this address and put it in the second address. Result. So there can be multiple instructions. So we want a way to represent all these things, right? How do we represent? So assume, so these are the different instructions, put, add, subtract, these are the different instructions. So assume I have 10 different instructions, then how many bits I need to represent this 10 different instructions? Anyone? So 10 different values are there, assume. How many bits I need to represent these different values?
2 power 9, sir.
2 power 9, right? So to represent two values, how many bits you need? To represent 2 power n values, we need only n bits.
So 2 power 10, sir.
No. So to represent 2 power 10 value, we need 10 bits. To represent 10 values, how many bits we need? So to represent 128 values, which is 2 power 8, we need 8 bits. Correct? So to represent 32 values, which is 2 power 5, we need 5 bits. Correct? So to represent 10 values, how many bits we need? Anyone? Okay, let's meet it. So to 8 values, how many bits we need?
So for 10 values means, see, for 8 means should we need 3 bits, sir?
Yeah, we need 3 bits because 2 power 3. So 10 is more than 8. So we need at least one more bit, right? Because we cannot represent 10 values with 3 bits. So it at least needs 4 bits. Yeah. With the 4 bits, you can represent up to a maximum of 16 values. But to represent 10 bits, you need that 4 bits also. Even though some bits won't have values associated with it, to represent these 10 values, you need 4 bits because you cannot represent 10 values with 3 bits. Correct?
Yes, sir.
So this is lying between this 2 power 16 and 2 power 8. So it needs 4 bits. Okay, at least 4 bits are needed to represent 10 values. So for example, we'll represent that values, and the last bits may be last possible combinations, the values for 11, 12, 13, and that things may be skipped. We don't have instruction to represent. We only have 10 instructions, so we can represent it like that. Okay, so I have 10 instructions, so I need 4 bits for that. I need 4 bits for that. So I also have other operands, right? So what other values? So like adding. So if I need 2 values to add, and I want to add 2 8-bit numbers, right? If I want to add 2 8-bit numbers, I want 16 more bits to represent, right? So add 5 and 6. Assume this is a command, and this number needs 8 bits to represent. This number needs 8 bits to represent. And to represent this add command, I need 4 bits. So how many bits I need to represent this whole instruction? 4 plus 8 plus 8. I am saying that my computer can handle up to only 8 bits. It cannot handle more than 8-bit number. Then I say the total instruction size will be 8 plus 8, 16, 20 bits. So my computer with this 10 different instructions can handle and has a size instructions of size 21. Okay. So these instructions are just made up instructions. Actually, every computer, every processor will have their own instruction set that you can see. Like there are this Intel processors will have their own instructions. Other processors, other company processors will have their own instructions, and RISC-V processors will have their own instruction sets. Those are there. Okay. But the theory is this: if you have this many instructions and your one operand need this much bits, and you are using 2 operands, this is the minimum number of bits that you need. Correct? Correct? Did you get how this works? How we can represent an instruction?
Yes, sir.
So we can make our own thing for add. So if I want to represent, so I say 0 means add. I say 1 means subtract. I say 2 means division. 3 means multiplication. We can assign it like that. Like we assigned every numbers and this character's value. We can assign it like that. So here assume I have only this 4 instruction my computer can handle, and my computer can do every instruction that my computer accepts will have of this 2 bits for the instruction to specify this instruction. And my computer, assume that my computer can do this operations on 16-bit numbers. 2 16-bit numbers it can handle. So what will be the size of instruction? 16-bit plus 16-bit. Correct. So my computer can handle this instructions. So my size of the instructions would be 34 bits. I need to represent. Okay. So actual computers have very definite set of instructions that you can see. So this RISC-V is the kind of RISC-V. People call this RISC-V instruction set is there. So there are many instructions. There is a whole very long book is there, having all these instructions and things like that. So you see this 1 bit. So this is 32-bit instruction, as you can see, and this is some operation. Some operation is there, and that code for that operation is in this first 7 bits and some other values, and each will have the number of bits associated with it. Okay, so this is the base instruction set, something like that, right? So you see this 31 bits are there. So this last bit says which operation it is. So you can see this is something like add, something like that. So there will be many instructions in the low level that CPU can handle. You can see this add I is there, kind of that. Okay, so each bits will be represented. So this is the source, destination is there, which means where to take the value and where to put the value, kind of that. So that will be represented in some bits. So this is how a whole instruction will be represented. So this you need not go into deep. Just assume this is how it is happening internally. Okay, any doubts?
No, sir.
Okay. So I think we have covered pretty much everything from week 2. Yeah. Okay. Thank you. Hello.
Sir, could you give a short note on OS alone, sir? Just like summary.
OS, I think this. So OS, okay. So you are writing this codes, right? You are running applications like the file manager, the browser, everything you are running, right? So, okay, let me see. So as far as we have seen now, there is only one processor, or nowadays the systems have many processors. So, but there is limited number of processors, right? So like 8 processors, maybe you have an octa-core processor, 8 cores will be there, which means it can only perform maximum of 8 tasks at a time. But we are performing many tasks in our computers, right? So how it should be distributed? So there are many things happening there. So what OS do is, what we say is that OS will be like this. Assume this will be your CPU, and you will have many cores there, and above that OS will be there. OS will be there. This is your CPU, and here your applications will be there. You run many applications, right? The calculator is also an application. Everything is an application. So what this does is, so we want all this to run equal time in these things, and we want to handle different tasks in a different way. So what OS does is, it allocates the processes. So for example, now for some time this process should run, and sometime this process should run. It will redirect the processors to the CPU and run it for some time and give it back. So actually this sometime is a time of size milliseconds or nanoseconds. That's how our today's processors are very fast. So we don't see that they are executing in one by one. We'll see that everything is happening in a very simultaneously in the same time. Actually, there are only limited number of processors and things happen. All these are controlled by bits. So if OS is not there, assume this app is running, your browser is running, and this may not allow your calculator or the file explorer to run. Okay, this will fully take the CPU. So there is something need to manage all this, right? So that's why OS is there.
Okay, sir. So OS is stored in ROM, so helps for booting.
OS won't be stored in ROM.
Sir,
Actually,
because...
it will be in your hard disk.
Oh, okay, sir.
Your hard disk is different from a ROM. So RAM is the volatile memory, which means it will store the programs that are running. So what will happen is OS will be stored in the hard disk. So when your computer turns on, that OS is loaded into your RAM. So when program needs to run, it needs to be loaded into RAM. Okay, programs will be in your hard disk only first. The running programs, which we call as process, will be in the RAM. All your
Okay, sir.
applications and all your OS will be present in the hard disk only in these systems, and that will be loaded into the RAM when your computer boots up.
Okay, sir.
Okay. Any other thing?
No, sir.
Okay. Then we'll stop. Thank you.
Thank you, sir.
Thank you, sir.